Hello, welcome to another cosmology talk. This week we have Clare Burrage, who is a professor at Nottingham University. She's an expert on a few things, but especially beyond the standard model stuff and its relevance to cosmology. But I especially like her work on using atomic experiments to detect fifth forces, specifically those with screening mechanisms. I was also thinking the channel was getting a little bit too kind of astrophysics and large-scale structure-y, so I thought it would be really good to have a few talks on the more like terrestrial stuff that's being done that's relevant to cosmology. I also really like this stuff because it kind of harkens back to a pre-21st century way to do fundamental physics where people are sitting there in labs, although I think the constraints might be getting sufficiently tight that these labs are starting to get quite big as well and quite large collaborations. And it also sort of suggests that maybe this stuff might be usable one day because you're not having to build gigantic particle accelerators just to discover it or observe the first fractions of a second of the universe. This is the first talk that isn't so much on just one paper, but on a topic, but I think it'll work quite well. So thanks, Claire, for joining us. Do you want to maybe briefly summarize what it is that you'll be talking about today?
Yeah, I think you've done a pretty good job of summarizing what we're going to talk about. But yeah, about the idea that you can test your theories of cosmology, not just with cosmological data, but also by looking for sort of carefully tailored observables in the lab. And yeah, mostly focusing on sort of theories of dark energy or modified gravity and their nonlinear dynamics, which kind of really lend themselves to being looked for in this way.
So if someone is looking back on this talk a few months from now, or your work in general, and you just want them to remember a couple of things from watching this, what would those couple of things be?
Yeah, so I guess first of all that there's lots of interesting physics to be explored in these theories. The theories we're going to go on to talk about they have a lot of nonlinear behavior, and that means that they do a lot of things that are very surprising. And also, yeah, just the power of a small experiment in one lab run by a handful of people to really kind of rule out theories that we're interested in for cosmology.
Cool. And then what is the kind of background motivation to your recent work and to this topic in general? What things were unsolved 2 years ago that are now solved, and that you wanted to solve? Why were they unsolved? That sort of thing.
I mean, I guess, okay, the big unsolved thing, which I absolutely have not solved, is to understand why the universe is accelerating, why the expansion is accelerating at the current rate. So that's kind of the underlying motivation.
Yeah.
But having said that, the theories that I'm interested in, I'm not interested in them specifically because they directly explain that acceleration. Some of them might do, or some of them might do in certain regimes of parameter space. But I'm more interested in the question of kind of, well, there's something really kind of fundamental that we don't understand about what the universe is doing on the very largest scales. So is there any new physics associated with that? And because that's coming from large distance scales in cosmology, because the cosmological constant scale is a low energy scale, certainly in the kind of compared to particle physics, you're thinking about new physics of light particles, of low energy physics, and of things that are maybe kind of connected to gravity or coupled to gravity or come from modifications of that as well. And so that's quite different to a lot of the ways that people look for new physics. When people talk about new physics, you think about the LHC and looking for the Higgs and looking for supersymmetry and things, things that are heavier than and this is new physics that's light and weakly interacting, and that requires a whole different mindset to think about how you look for that.
Right. Yeah. In the near past, what were the kind of specific problems about this?
Right. So the history, I guess, is that people have thought about introducing new light scalar fields to explain dark energy for a long time. Like that's a super well developed field. But the problem always was that you had to explain why they weren't interacting with matter, because as soon as you have a new light scalar field that interacts with matter, you would expect to get a new long range force. So you had to come up with some explanation for why you hadn't seen that. And that was quite difficult to do, or at least to do without just saying, okay, I'm going to forbid it from interacting, and that's just the way things are. And then in the, I guess, early 2000s, people started thinking about, as we said, thinking of these theories as being nonlinear.
Mm-hmm.
And as soon as you do that, you realize that actually everything opens up again, because suddenly you have all sorts of interesting ways in which your scalar field can hide from the experiments that otherwise would be so constraining for it. Mm-hmm. And so there was this sort of change then from these theories kind of like they either can't interact with matter or they can't exist, to, oh, well, they can interact with matter and they can have all these different coupling strengths and all of this different behavior, but it's all set up so that we can never see it. Mm-hmm. So suddenly you've got some really interesting new physics and no way of looking for it. So that was really the puzzle, and the thing that I guess drew me in was, well, we've got these really interesting theories that we're proposing and they're sort of designed so that we can't see them. Mm-hmm. Is there a way around that? Is there something?
And I guess you'll get into this pretty soon, but the screening is related to the density, right? So that's why we can't see it. And then I guess you need to find a vacuum on Earth to try and see it. But yeah, so maybe you want to now start getting into the details, and if you want to bring up slides.
So this is the motivation for, certainly for the type of experiments that we're going to talk about, is the idea of testing the equivalence principle. So fundamentally, do large and small objects fall at the same rate? And our expectation, certainly, as you know from standard physics, is that they should fall at the same rate under gravity. Mm-hmm. But what we're going to see is that these theories of dark energy, or kind of modified gravity, or scalar fields kind of related to dark energy, they give you a reason to expect actually that under certain circumstances, light objects or small objects would fall faster than large ones, that they feel an additional force, essentially, or they feel a force more strongly than the heavier ones. And the interesting physics is to say why that only happens under certain circumstances. Obviously, if it happened all the time, we would have been able to rule it out already, because we think we have pretty good tests of the equivalence principle so far. But yeah, this is to try and see if you can draw out this behavior where you can see this extra force acting on smaller objects more strongly. But the standard story, and this kind of gets back to what we were talking about before all of this nonlinear behavior was understood, before we talked about screening, the standard picture was do the simplest thing that we can do in theoretical physics, which is we add in an extra scalar field to our model, and we use that to try and explain dark energy. And then if that couples to matter, we can look for the fifth forces that it mediates. And so this is just one plot from the very nice review by Eric Adelberger of one type of way of searching for that the existence of that light scalar field. So this is saying, okay, then in addition to the gravitational potential, there's an additional potential which is mediated by my scalar field, and my scalar field has a mass, and it couples to matter with some unknown constant alpha, which we normalize to the gravitational scale. And then the constraints that we have on Earth and within the solar system are extremely good. That parameter alpha is very, very constrained. And this was kind of the problem, that on the one hand you had cosmology kind of really motivating introducing a light scalar field of this form, and then on the other hand you had all of these amazing experiments that said no, it can't be there. We searched for it and we don't see anything.
So the tightest constraints are on this kind of 10 to the 8 and above, I guess. Mm-hmm. But it looked, I mean, at 1 meter, it doesn't look super constrained. But would it just be that it kind of should be there at the 10 to the 8 meters because that's the value of m phi, or?
Right. So this is, I guess, more of an illustrative plot a little bit, okay. rather than the whole story. But yeah. So this is saying if you have your fifth force, so that with the mass, your scalar field, so that the mass of the scalar field corresponds to a Compton wavelength of this order. So so you could think of the horizontal axis as being 1 over the mass of the field. Yeah. And then so these tight bounds are on particular values of particular choices of the mass for the data. And this is more just illustrating the power of kind of what we can do, then really, kind of, yeah.
Cool.
But the point here, and why kind of this form of the potential that you get is illustrative. As you can see, in this case, you only have two parameters. You have the mass of the field and you have the strength of the coupling, and they're fixed. And so you can go out and just kind of test a whole bunch of different distance scales and see if you can see any deviation from gravity on those scales.
And show the constraints in a two-dimensional plot.
Yeah, exactly. Yeah, it makes your analysis much easier. But because you're working with a scalar theory, it's not charged. There's no reason to forbid it having more complicated interactions either with itself or with matter, in fact. And as soon as you do that, oh, sorry, wrong way. As soon as you do that, you actually get, as we were saying, a whole bunch of much more interesting behavior for these theories. Essentially because what you have now is it's nonlinear, so fluctuations are affected by the background. They don't decouple anymore. And so now the properties of those fluctuations, like their mass and their coupling constant, is affected by what you think the background is. And so then you can start to think about arranging for your field to have one set of properties in one environment and a different set of properties in another environment. And then kind of the two characteristics that are most relevant to the experiments I'm going to talk about are, you can imagine getting in a local environment a much larger mass for your field. So your field could be light in some environments and heavier in others. Or you can imagine changing the coupling constant, so you're more strongly coupled in some environments. Yeah,
and this is no more complicated than the Higgs value changing and therefore the electron mass or whatever changing. Yeah.
Exactly. Okay. Or the way you get Debye screening of electromagnetism in a plasma, where your photons get an effective mass, and that limits the range over which you can transmit electromagnetism. Yeah.
Cool.
So yeah, the fact that nonlinear physics does interesting things is certainly not new. There's a third case where you play with the kinetic structure of your theory, but I'm probably not going to talk about that today because it's not as relevant for the experiments.
Okay.
So the kind of the archetypal model of this kind of behavior is known as the chameleon, and so it certainly was kind of first written down by Justin Curry and Amanda Weltman. As we can see, at least in terms of scalar tensor theories, a chameleon is a scalar field that has standard kinetic term, it has some choice of potential, and then some function which controls how it couples to matter. And I've kind of already assumed that my matter is non-relativistic and described by a perfect fluid, but you put the whole standard model in there if you want to couple it together. So we're going to pick a linear coupling to matter, but a more complicated choice of potential. So this is where all of our nonlinear behavior is going to come in.
Okay.
And this inverse power law potential is one that was kind of chosen in the initial model because at the time people were using these runaway potentials to do kind of runaway quintessence models. And it's kind of a nice illustration, but the kind of behavior that we get isn't very certainly the type of behavior we get isn't very sensitive to the choice of potential. As long as you've got some nonlinear structure in there, the kinds of things we're going to see will happen, although obviously like precise constraints depend on
and I guess at this point, or certainly perhaps in 2004, but at this point of kind of like the developing the complexity in your talk, the 1/5 potential, it's not something that sort of pops out of some more complete beyond the standard model thing, like I don't know, like the MSSM or a sterile neutrino or something. It's just kind of like, here's something that may pop out of something, but we're just looking at the phenomenology, or is there like a really good reason for a 1/5 potential?
No. So people have tried quite a lot to build models like this from string theory or from some more UV complete theory. There are some suggestions that you can do that. There is at least one paper that claims that they to have built a chameleon model from a string theory scenario. but it's pretty challenging. And I'm not going to be able to remember the authors, but if you want the reference, I can give it to you.
Yeah, but maybe I'll make a note and you can email me and I can add it in the description.
Sure.
Yeah.
But in general, yeah, it is challenging to build these theories from more UV complete theories, and some of it is the cosmological constant problem in another guise, because some of the problem is just that you still have to have a massive hierarchy of scales in your theory.
Okay, but the actual potential isn't the problem; it's the coefficients that is the problem.
Yeah, okay. but I mean, we could have picked lambda phi to the 4 for our potential, for example. Okay. Yeah, the fact that it's kind of so pathological is not necessary.
Okay,
yeah.
Okay.
More easy. Okay, so then once you've started from this theory, then the behavior of your scalar field is governed by an effective potential, which is composed of those two pieces that we've just been talking about. So the bare choice of potential that we chose, and the coupling to matter, which is our energy density rho. And then you can see immediately that when you sum those two things together, you get an effective potential that has a minimum. The position of that minimum depends on what you choose the density to be, and the massive fluctuations around that minimum changes as you change the density. In particular, this is exactly what we were talking about: a field that becomes more massive in a dense environment and less massive in a diffuse one. So that's where the structure of this behavior, of this varying mass, comes from. So then there's the question of how does that hide your fifth force? Because we've got a scalar field, coupling to matter, we should have a fifth force in theory. And so this plot is a little bit complicated. Okay. But the point is that if we want to think about what is the potential mediated by our scalar field, or the potential of our scalar field around some massive object, so that we could then compute the force on a test particle. And we're going to take our object to be some spherically symmetric object of constant density in some constant background. Okay. So there's two forms of the potential that are useful, or that are relevant here. One is where we have the background density and the field wants to live here. And the other one is when we take the density inside the object, and then the field wants to live kind of at some smaller value here. So you start far away from your object outside, it's happily sitting in this minimum with the larger value of phi. And then as you come closer and closer to the surface of the object, at some point when you get to the surface, that density suddenly increases and you jump up to some point up here on the potential, the field jumps up. And then it's going to roll down towards smaller and smaller values. And that is the standard story that would happen. It's essentially what happens for a Yukawa type fifth force. And in that situation, if we were talking about linear physics, nothing would stop the field from rolling, and just inside the object, the field rolls to smaller and smaller and smaller values. So what's happening here is that our choice of potential, which in this case is our inverse power law, kicks in and stops the field from evolving past some particular point. The field gets trapped inside. And then you can see, so you've got one value for the field at infinity, and essentially another value for the field in the center of your object. And that limits then how much potential you can build up. You could keep putting more and more mass into your object, but you wouldn't be able to move the field any further. You wouldn't be able to move it to a smaller value. And so the amount of potential that you're able to build up is limited, and so the gradient of that is also limited, and that's why your fifth force becomes weaker than it would if you didn't have these non-linearities.
I have one question that feels like a stupid question, but it might be one of these stupid questions that's actually not a stupid question. If you were to tell me go and measure the density of something, in some sense that becomes a coarse graining dependent answer. Like if I zoom in, eventually I'm just going to see a bunch of particles, like of water. If you say, what's the density of water? If I zoom in far enough, I'm going to see a bunch of water molecules. Yeah. So what density is it here that is relevant? Like, I mean, you said, you're assuming it's a perfect fluid, and if it is a perfect fluid, then okay, it's not a coarse graining dependent thing. But if it's, water or whatever this core and shell are made of,
yeah,
what is the
no,
relevant
it's not a
density?
stupid question at all. It's a very good question, and something that has to be thought about very carefully, and you have to check. Otherwise, at some point you're not doing a consistent calculation anymore.
Right.
So what I can say is that in the types of experiments that we're going to be doing, the relevant densities are going to be of the order of grams per centimeter cubed. And they're, well, I mean, it's going to depend where you are in the parameter space, what your Compton wavelength is of your field, so what the averaging scale is, but it could be as large as a millimeter or a kind of tenth of a millimeter or something. Okay. So you can get this behavior without necessarily having to resolve kind of really atomic scale physics. I see. But that is a consistency check that you should always do. Yeah. So we have with two of the postdocs in Nottingham with Ben Elder and Pete Millington. We have a paper from probably 18 months ago, where at least in two dimensions, in one spatial dimension, this has actually becomes really easy. That anything that you can't resolve structures or variations in density below the Compton wavelength, and you can resolve distances or changes that are scales that are larger than the Compton wavelength, and you see how this arises with the 1D case is more tractable analytically, which is why it's easy to prove. We're working on doing it in the fully three-dimensional version as well. Yeah, okay. So this is really kind of the fact that you have this region inside your object where you can't build up any extra potential is kind of the underlying reason why you can't create larger fifth forces for larger objects in these theories. But then you sort of can start to see, well, if I had a small enough object where the field doesn't even roll inside all the way to this minimum, then I don't have any of this. I don't see the nonlinear structure of the theory. So it should just behave like a standard power type fifth force, and then there's no suppression compared to what I would ordinarily expect. And that's the origin of the equivalence principle violation in these theories. That small objects, if an object is sufficiently small, where small is something we can quantify, it behaves in the standard linear way, and it's only when objects are large enough that you get this nonlinear behavior, but it's the nonlinear behavior that suppresses the fifth force. Okay.
And I guess this is when it's immersed in a background that is sufficiently not dense that the background itself isn't.
Yes, absolutely.
Making the chameleon.
So in fact, you could argue that a lot of why you wouldn't see these effects in the solar system is actually because the background is sufficiently suppressed by the density of the Milky Way.
Oh yeah. Okay. Cool.
So this is basically just saying the same thing in equations. So I might just skip forwards. So then the point is, if you can come up with an experiment where you can look for the fifth forces in the unscreened regime, if you can find a test object, a test body that where the fifth force isn't suppressed, then you're going to be much more sensitive to its existence. And this was kind of one of the key things that meant that we started off on this project was realizing that atomic nuclei have exactly this property. So atomic nuclei are obviously very dense, but they're also very, very small. And it turns out that the smallness wins in this sense, and that over a lot of the parameter space that we were interested in, they would be unscreened objects, and so they would feel the full strength of the fifth force. This is a project that really kind of came about serendipitously, in that I moved to Nottingham, where obviously you know Ed Copeland, and Ed used to be at Sussex with another Ed Hines, who is a really kind of an amazing expert on cold atoms and experimentalist. And so we got talking, and the idea of whether you could do anything with a cold atoms experiment came up. And then, as I said, we realized that atoms are actually really good probes of these forces, at least in a laboratory vacuum. So kind of when we started thinking about this in 2015, this was the sort of parameter space that was open to these theories. So and this is what we were saying, that they were just so unconstrained at the time. So we had two energy scales in the theory. We had the strength of the self interactions of the scalar field theory, which is kind of what's on the vertical axis here, normalized to the cosmological constant scale. And then we have the strength of coupling to matter, normalized to the Planck scale, which is on the horizontal axis. You've got 14 orders of magnitude on one axis and 4 on the other. And that was all kind of open to you. Essentially, all of that was open to you at the time, or a few little corners. And so everywhere kind of above and to the right of these dashed lines, atoms would be really sensitive probes of this force. So we had a really good shot at getting at a huge chunk of this parameter space. Then I've got a couple of slides on introduction to how atom interferometry works, if that's something you want to go into.
Yeah, why not?
So yeah, because once you realize that atoms are a good test object for these theories, you still need to know how to measure the force on individual atoms, right? We really want to drop in individual atoms and measure their forces, and that's what atom interferometry allows you to do. But yeah, you're building an interferometer, and the waves that you're interfering are atomic wave functions, essentially. But in all other senses, this is the same kind of interferometer as we're used to talking about in all sorts of other areas of physics. And you separate spatially those wave packets by essentially poking them with lasers. So you've got your atom, you've got, if we talk in the sort of simple version of this, the abstract picture, if you imagine a two-state atom, and your atom's in the ground state and it's at rest as far as the experiment is concerned. You shine a photon on it to give it just enough energy to excite it to the excited state. As the atom has absorbed that photon, it also has to absorb the photon momentum. So that we get conservation of momentum. So now you have an atom in its excited state that's also traveling with some velocity.
Makes sense.
But if you set this up in such a way that you don't make an observation of the state of the atom, you can now have your system in a superposition of states, one of which where your atom didn't absorb the photon, and so it's in its ground state and it's rest, and one of which is where your atom has absorbed the photon, is in an excited state, and is also traveling with some velocity. So to build an interferometer, you essentially only need to do that. You need to do that 3 times. So this is a sketch of where your atoms would be as a function of time. So they all start off in the same position. You shine the laser on it once. Those are the squiggly lines. Separate it into two states. You shine the laser on it again to give the atoms a kick. Oh, sorry, the parts of the wave function kicked back towards each other, and then a third pulse to recombine them. So this is really your beam splitter, your mirrors, and your recombiner.
And what's happening at 3? Is that like stimulated emission so that it gets a downwards kick, or?
Exactly.
Oh,
yeah.
Okay, cool. And gravity is what's causing the parabolic shape, and I guess or gravity plus the fifth force.
So that's the other yes, exactly. So that's the other piece of this diagram, is that we're assuming that there's some constant acceleration downwards in the x direction. And then as the 2 parts of the wave function travel along the 2 different paths, they accumulate phases, and those phases are what you interpret at the end of the day. And if the acceleration that your atoms have experienced is a constant, then it's actually quite a straightforward calculation to be able to say that the probability of measuring your atoms to be in one state or another is a trigonometric function of the k was the wave the momentum of our photons, a is our acceleration downwards in the x direction, and then t is obviously the time between the pulses. So this is really kind of school level parabolic motion, and then just sort of counting up all the accumulated phases and then taking the difference.
So 10 years from now, after this fifth force has been detected, this will be a high school assignment problem.
Exactly. So yeah, so what if you can measure the state of your atoms at the output of your interferometer, then you have a really, and you obviously you're controlling the photon momentum and you're controlling the time between the pulses. So then you have a direct mapping to the acceleration that you're at. So then you just need to do it really. The only thing that was different for looking for these looking for screen phase forces compared to what people have done before, because obviously atom interferometry is a much older technique than the experiments that I've been involved in. And people have been using it also to test gravity beforehand as well, to try and measure big G and measure kind of the local gravity and look for equivalence principle violations. But what it turns out is important for us is that all of those experiments have put the source mass, or what was sourcing your gravitational field, whether that was the Earth or some other object in your lab, that had been outside the vacuum chamber. And it turns out that just the walls of the vacuum chamber are enough to suppress our field, to make it really heavy again, because the walls are still there. That you can't transmit the Chameleon force or the screen force through the walls. So you have to put the source mass inside the vacuum chamber. So that so this is then just a sketch again of kind of what your Chameleon field is doing. So we're imagining some kind of spherical vacuum chamber. So if there was nothing inside it, the field would just rise up to some central value and then fall down again towards the wall. And then we put a source mass in there in one of two positions, so that you get some gradients at the center of the chamber, and then that's where you have your atoms, and see if you measure the force.
Okay.
So this is a photograph of the experiment at Imperial. Just first to prove that it exists, and secondly to remind me to kind of really make it clear that I'm not an experimentalist, right?
Okay.
There was a very impressive team of people at Imperial who did a really excellent job in putting together and carrying out this experiment, kind of led by Ed Hines. He's done a really good job of measuring this stuff. And yeah, this is the data we got for the different runs, but the kind of conclusion is that we don't see any anomalous acceleration at this level. So if an anomalous acceleration is there, it has to be essentially smaller than kind of order 100 meters per second.
Okay.
So this is the same parameter space we were looking at before. So we've got our two parameters, the self-coupling of the scalar field, and that's normalized to the dark energy scale. So if you wanted to have the most direct connection to this being new physics, which is associated with the cosmological constant scale, then that's where you would expect it to live on this.
And is this for the self-coupling being that lambda over phi, or
exactly?
Okay.
Yeah.
And is this? I presume you could just have a separate plot like this for a whole bunch of different potentials relatively straightforwardly.
Yeah.
I mean, at least that would be work the theorist would have to do. You wouldn't have to build a whole new Imperial College lab.
Yeah, no, the experiment just constrains the acceleration, and then you can turn it into constraints on whichever model you want. I can't remember if I put constraints on any other potential form of the potential in the slide. I might have a backup slide.
If the conclusion is broadly the same, then that would be unnecessary.
I mean, yeah, certainly. I guess the main conclusion is that these are extremely constraining experiments, and that's true for any choice of potential.
Yeah. I mean, just looking at this, it looks there's a tiny sliver, I guess.
Yeah. So yeah, if that's the lambda at the dark energy scale is kind of where you would like, or where maybe at least you would first expect to live. And then the coupling to matter on the horizontal axis, again, if you're thinking of this coming from some modification of gravity, then you would expect maybe m of order m Planck or somewhere around that. So you're sort of expecting kind of this region here to be the most physically interesting. and obviously torsion balance constraints, kind of pre-existing constraints on this forces ruled out some of that. And then kind of the atom interferometry experiments have come in and really wiped out a huge part of what was left.
And what does the hydrogen bar mean?
Right, so the hydrogen band is actually, so that those are theories that are so strongly coupled that you would get a fifth force between the nucleus of hydrogen and the electrons in the orbitals.
Oh, wow. Okay.
And you would perturb the atomic structure to a point that you could measure.
Okay.
You could see that. It's actually really interesting to me that, so we also kind of worked out what the constraints from collider physics would be, because that you would also expect that to come in at the very, very strongly coupled end, and actually the hydrogen spectroscopy measurements are more constraining for the strongly coupled theories than collider physics are. So yeah, so I guess the other thing to say is, so the blue shaded region is the results of the experiment that we did, or that the guys at Imperial did. So that's the kind of most recent work currently that I've done on this topic. But there is, as you can see, a very closely related curve, which is a group at Berkeley who saw our original paper proposing that you could do this kind of experiment to search for these models, and they did. It's not an identical experiment, so it's really nice to kind of have these two complementary. They work in slightly different ways, different atoms, different orientations of the experiments, like that. So got a very kind of compelling constraint here from two different.
I mean, I don't know how much more you want to talk about, because I have even more questions about just this figure, but I mean, maybe I can just get at them out later. But there's two interesting things I find about this figure. One is that their result is so identical to yours, which is very suggestive that somehow, like, there's some laboratory limiting thing that both groups have run up against that just is a really hard boundary, and that some new technology is going to be needed to improve this. And then the second thing is I just wanted to know what the shape of it, like there's a downward horizontal and then a horizontal and then a kind of going up one. What is the physics behind that?
So the answer to the first part of the question is, it's actually also, the lines are also roughly where we forecast you could get to. So it's really, it's not a hard limit of what is physically possible, but it's the level to which you could reasonably straightforwardly control your noise and systematics, at least at which it was already known that you could do how to do that to that level of sensitivity when we proposed the experiment in 2015.
And then the shape is the other interesting thing.
Right. So this plot is roughly showing you the same parameter space, and we said above and to the right of the dashed lines, the force was unscreened. So there are regions in this parameter space where even the force felt by an atomic nucleus is screened. And that's the transition. That's the first transition that we were looking at here between this the kind of the slope of the curve that's sloping down and to the left, and then at the point at which it flattens off is the point at which atomic nuclei become screened. And it's sort of relatively straightforward, looking at the mathematics of how the screening works, to see that makes your constraint then become independent of the coupling constant. And then another property of the theory that we haven't really talked about, but it's also in this earlier plot, is the background value of the field. I mean, we talked a little bit about how kind of the amount of screening you get depends on what value it's trying to reach, or what value the field would like to take if there wasn't an object there, and the value it's trying to get inside the object. And you can see, so that's what's plotted actually in the rainbow colors in the background, and you can see that value kicks up in this bottom left-hand corner, which is to do with whether or not your vacuum chamber is large enough for the field to really get to its potential inside.
I see. Okay.
And so it's that kick up in terms of the background value which causes this kick up.
I see. Okay.
and then it gets cut off at this point. So the vertical line here is because that's the point at which the walls of the vacuum chamber no longer are good at separating things that are happening outside the vacuum chamber from things that are happening inside.
Okay. Okay.
And so we just don't extrapolate our constraints into that region.
Right. Okay. That's really really useful, and it also sort of shows, in order to improve the various masses, what experimentally one would need to do.
Exactly. Yeah. So then actually here, I did keep it in. So this is the lambda, just to show you a different choice of potential. This is the lambda 5 to the 4 potential. So these are figures from slightly older. So Jeremy Sackstein and I wrote a review of the constraints on these models. Jeremy's really an expert on all of the astrophysical and ways of testing these theories. So this is essentially, the plot on the left is essentially the one we've just been looking at, and then the one on the right is for the lambda 5 to the 4 potential with lambda on the vertical axis. Right. So again, you can see actually those theories are also essentially kind of ruled out for the kinds of interesting values that you might want to pick. Yeah, so that was everything that I kind of put together today. You can go through the summary if you want.
Yeah, I mean, why not? We've got a little bit of time.
Yeah. So kind of what we've done over the last few years is to really take seriously the idea that dark energy, or the accelerated expansion of the universe, motivates the introduction of light scalar fields, and that those light scalar fields want to mediate long-range fifth forces, but that we don't see them kind of within the solar system or in previous terrestrial laboratory experiments. And the reason for that is that there's a screening mechanism operating, which is the idea that the theory is nonlinear, and those nonlinearities kind of act to hide the fifth force in certain environments and for certain sources. But the key point that I kind of want to stress is, just because these are theories that like to hide doesn't mean that they're impossible to detect. You just have to think of kind of suitably designed experiments or observables to look for them. And it turns out, particularly for these chameleon type models, that atom interferometry is a really powerful technique for doing that, and really gets at already kind of most of the interesting parameters for these theories. And it would only take a little bit more of a push to kind of rule out kind of everything that one might realistically think was interesting.
Yeah, like that last point was actually a question I wanted to ask. Like, is this it? Should people give up on talking about modifications to gravity, or a scalar field that looks like a modification of gravity, in order to explain dark energy? Like, it might still be that one has a belief that whatever can happen will happen, so there may be a fifth force that isn't dark energy, and dark energy is just a cosmological constant. So it doesn't mean you should stop doing atom interferometry to look for fifth forces, but has it reached the point where you just have to start adding bells and whistles to avoid the atom interferometry, such that it stops being at all compelling? Or are there like some compelling things still out there?
So I think it's certainly true that these constraints are most powerful for these chameleon type models. And when we started talking about screening, we talked about 3 different types. One's where you change your mass, one where you change the coupling constant, and the other one where you change the kinetic structure of the theory. So the ones that are most ruled out by these experiments are the ones where you change the mass depending on the environment. And those, I would say, there is some region of parameter space left where we don't have constraints, so they could still live there. But they're certainly under pressure now from the experiments.
And that region did look very small in those couple of figures, so it would be a coincidence. I mean, maybe it is a coincidence, but it would be a coincidence that
I mean, you could argue that region of parameter space is still very close, is still within what you would probably previously have said was the most interesting region of parameter space, or the easiest to motivate, in the sense that one coupling is close to, your coupling to matter is close to gravitational strength, and your self interactions are kind of close to the dark energy scale, which is at least what you're trying to explain. So it's not necessarily a really unnatural part of the parameter space that's left, but it's still a small window.
Yeah.
Yeah.
So it wouldn't be fine tuned if it lay there, but it would just be a coincidence that the earthly experiments
That was the
happened to.
hardest.
Yeah. Yeah. Okay.
Yeah, the hardest.
One of my other questions is something that you were almost touching on there. So you said that the ones that have been constrained are the ones with the mass changes. Is there a way of also designing clever atomic experiments to test these kinetic parts of the Lagrangian deviations?
So the kinetic screening ones are and this is now just my opinion, but I think the ones that are going to be hardest to test with laboratory experiments, because screening there works in a very different way. It's more the case that if you have some compact object like we've been talking about, that the fifth force is suppressed within some radius. So you go far enough away and you see a totally unscreened fifth force. But as you come closer and closer, the nonlinear kinetic structure of the theory plays a role, and that's what makes it harder to build up gradients in your potential well.
Okay. And
so that happens inside some radius. But that radius can be much, much larger than the object that you're interested in. So sort of typical values that people talk about are, if you're thinking about a galaxy cluster, then maybe the size of the fifth force is suppressed everywhere inside the galaxy cluster.
Okay.
For the sun, maybe it's suppressed everywhere inside the Milky Way kind of thing. But you get crazy scales and so crazy suppressions. Okay. So I haven't seen yet any kind of really. I mean, you still can work through what all of those suppressions are, work out what the constraints are on the theories, but they're not super tight. And I haven't seen. I haven't thought of a good way of getting around that.
Oh, yeah. So one other question that I was wondering about whether you'd bring up, but when I was sort of checking your name on the archive to see if you'd had any really, really recent papers on this, I did see that like you were part of a long list of names on a couple of very large collaboration atomic experiment. I think they were just proposals, but is that related to this? Is that interesting? Is that something you want to briefly talk about, or?
Yeah, I certainly can. I mean, as you said, there are but a couple of proposals to use atom interferometry much more broadly to look for new physics. I mean, there are all sorts of things you can do with an atom interferometer. I mean, basically what you built is a very, very precise accelerometer. So obviously you can use that to measure a bunch of different things. But in particular, things that people are interested in are gravitational waves and different types of, some types of light dark matter. You could think about looking for with an accelerometer as well. And so kind of looking for dark energy would then be kind of just would fold into the broader kind of science goal of building a big interferometer or a big network of interferometer kinds of things. So people are proposing at the moment, and we have to keep our fingers crossed.
I presume that they'd still cost a lot less than like a new particle accelerator or new telescope in space. So
yeah, no, absolutely. Yeah, I mean they're it's a scale up from what we've done that we've just been talking about here, but yeah, still on the scale of a particle collider, nothing else.
Yeah. I guess we've sort of been covering this over the last couple of minutes, but if you've got any other thoughts about where to next, I mean, I guess to some extent it's you've ruled everything out, so there isn't anywhere to go next. But I'm sure that there are other things that.
So the thing, certainly one of the things that is really interesting to me at the moment is so we've been talking about these theories as theories of modified gravity or kind of classical scalar fields that we've introduced through cosmology. But I got quite interested in sort of the microphysics of the theories and really understanding how they interact with the standard model. And it turns out that they're essentially equivalent to a scalar field that couples to the standard model through the Higgs portal. So you can recast the theory as just the Higgs portal coupling. And so actually they're equivalent to a lot of things that people study for particle physics reasons or theories of light dark matter. And so I've got quite interested at the moment in kind of seeing how much of what we've learned about the phenomenology and the behavior of these theories when we were thinking about them as dark energy actually applies to what is essentially the same theory when you're thinking about it as dark matter or something else.
So it might even be that these atom interferometry experiments have accidentally derived constraints on light dark matter without anyone realizing.
Yeah, quite possibly. Cool. So we just need to to understand that connection. And
cool. Okay, yeah. So the last question, outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
That's a tricky one. I mean, I think I'm certainly following the H0 tension with a lot of interest.
Right, yeah.
I do not have my own hypothesis for what that explanation is, but and I'm still agnostic about whether there is new physics there or whether they're systematics. But it really seems like it's exciting because there's something that we don't understand. Even if it's systematics, there's something there that we don't understand. And I also think it's exciting because it's just sort of driving people to look again at things that we've taken for granted, and reassess. Well, actually, is there scope for interesting new behaviour in the early universe, or are magnetic fields playing more of a role than we thought they were? And that I think is really interesting as well.
Yeah, that's a good point you made about it is pushing us to sort of like examine everything that little bit more carefully. Yeah.
Which I think is a useful exercise, even if it doesn't help.
Yeah, it's the sort of thing that a lot of the time people want to do, but if there's no like experimental force driving it to be done, it's not seen as valuable research. And now it is seen as valuable research because it's, even if it doesn't turn out to be the explanation, it's valuable to know that it's not the explanation. And then that paper is sitting there for 10 years from now, someone can still look at it and not have to read it themselves.
And know actually there is no room for early dark energy or whatever.
Cool. So thanks everyone for watching. If you like this, please do subscribe, and you can click that bell if you want to be notified of by YouTube about new things, and click like and share the channel with colleagues. And if you have any questions or suggestions, leave a comment. I'll make sure Claire sees the questions. Also, while you're here, you can watch another video. And thanks again, Claire, for a really insightful talk.
Thanks, Sean. That's been fun.